All right, good morning, everyone. Today we're going to talk about spectroscopy and the Bohr model, but we're going to give it a few more minutes for more people to join the YouTube live stream first. As a reminder, please also join the Zoom meeting that is running at the same time. That will help us let you guys work and do practice problems together more easily. So please also join the Zoom and accept all of your invitations to breakout rooms. Okay, we'll give it 1 or 2 more minutes to get a few more viewers, and then we'll go ahead and get started. Okay, great. So we're going to go ahead and get started. So today we're going to be discussing spectroscopy and the Bohr model of the atom. So first off, I wanted to review some of what we've done this week. So one of the main important relationships that we learned about was that the velocity of a wave is equal to the wavelength times the frequency. And I just wanted to quickly clarify one sort of general concept about waves that several of you had issues with on the problem set. So waves can travel both in time and distance. So for example, in this plot here, we're seeing our wave oscillate and the x-axis is in meters. But you could plot this same exact wave as a function of time instead. And that's how you would get your frequency information, and your period information is from the plot of the wave as a function of time. Whereas you would get wavelength from a plot of your wave as a function of distance or meters. And then another important principle is that waves are additive, and they don't have to be exactly lined up for this to be true. And another word for lined up is in phase. So the waves could be out of phase, and then you would still add them just like normal. So what you would do is for every x value on your graph, you would look at the y value of each of your two waves, and you would simply add them. And that's how you would figure out if your wave is constructively or destructively interfering. So hopefully in the last few days we've cleared up some of those concepts. And then yesterday we learned about some of Max Planck's theories. So what he said was that all energy is exchanged in small discrete packets called quanta. And this means that only discrete values of energy are possible. So another way of saying this is that energy is quantized. And then he proposed the following relationship to describe this concept. So he said that the energy must be equal to Planck's constant times the frequency of your radiation or matter. So just to review what this means, we can consider an ice cube. And initially, this ice cube will have some energy. And then say you put your ice cubes out in the sun, and they absorb some of the radiation that comes out of the sun. So this radiation has some characteristic frequency, so then we can use Planck's relationship to figure out how much energy is in this radiation. So then once the ice has absorbed this energy from the sun, it has a new final energy. And what Planck says when he means that energy is quantized is he means that these initial and final values cannot just be anywhere. They have to be at some discrete value that is an increment of h times f, which is the frequency. So hopefully that clarifies some of what quantization means. So moving on today, we're going to specifically talk about the visible light spectrum and how we can use that to get information about atoms. So the visible light is just a small portion of the electromagnetic spectrum. And this is the only part that's actually visible to the human eye. So if you look at the entire electromagnetic spectrum pictured on the slide, you see that it goes all the way from 10 to the -6 micrometers to wavelengths that have 10 to the 7th micrometers. And in there, you really only have a window of around 300 nanometers where you actually see visible light. So this really is a very, very small portion of the spectrum. But this is a really important tool for us to learn about atoms. And we can see here that each color of visible light actually has a characteristic wavelength. For example, we see that at around 700 nanometers, we get red light. But at around 480 nanometers, we see blue light. So this is a really important tool because that means each color of light has a characteristic wavelength, and only that color will have that particular wavelength. Okay. So let's talk about absorption and reflection of light. So when we observe colors, what is actually happening? So you would have light, and what our eyes actually see is the light reflected off of other objects. So this is the only color that we would see with our eyes. So say you had a white surface. What are we actually seeing? Well, white light is actually composed of all of the colors of the rainbow. So when we see white, that means that all of the colors from red, orange, yellow, green, blue, violet, they're all coming and they're hitting some surface, and then they're reflecting off of that surface. And then our eyes are able to see this entire spectrum of colors. However, we only see white, but white is made up of all of the colors, all of the possible colors. On the other hand, we also can see black. So exactly what is black light? So imagine you had your same white light that was coming in and it was hitting an object, but this time this object was a black surface. So a black surface will actually absorb all of the wavelengths of light. And since all of those wavelengths of light have been absorbed, that means no light is reflected. And when no light is reflected, our eyes just see black. So hopefully that can show some of the difference between absorption and reflection and how that changes what colors we actually observe. Here's one more example. So say we still had our same light bulb that was shining light onto a blue surface this time. So again, we would have all of the colors of the rainbow coming and hitting that blue surface. However, all of those colors would be absorbed except for blue. And then the blue light would hit this blue surface and it would reflect off that surface. And then what our eyes actually see is this blue light. So we can use some of these principles to actually study materials. So generally, this is called spectroscopy. So what happens in this example of visible light spectroscopy is that you have some hot gas that's emitting light. You can pass this light through a prism where you then kind of expand all of the different wavelengths so you can actually observe them. And then you have a detector that allows you to separate what each of these different wavelengths are. And this is a really important tool because we can study what wavelengths of light are emitted and what wavelengths of light are absorbed by substances. And just one quick comment about the difference between emission and reflection. So before we talked about how light is reflected from surfaces, and that's what our eyes see. So reflection is if you have an incoming light that's bouncing off of a surface, so it's reflected. Emission is when you have light that is coming from the object itself, but it still is light that's exiting the object. So it's similar to reflection, but there's a slight difference. But if it's helpful, you can kind of think of emission as a sort of kind of reflection. Okay. So let's think about some example spectra. So say you have a light bulb that emits white light. And we know that white light contains all of the colors in the visible spectrum. So we can pass this light through a prism. And what this prism will do is it will separate all of the different wavelengths of colors so that you can see what the individual ones are. And that would give us a spectrum that looks like this. So this is called a continuous spectrum because you can observe every single wavelength of light. And there are no gaps. We get a very smooth transition from violet all the way down to red. However, we can run a few different experiments. One, we could have a hot gas that's emitting light because it's a hot gas, so it's like trying to release energy. And we could pass the light coming from that, again, through a prism. So this time, something really unexpected happens. So we would get a spectrum that looks like this. So in this spectrum, there's only a few discrete lines, and the rest of the spectrum is black. So what this means is that we only are getting certain wavelengths of light that are emitted from our gas. So this is not a continuous spectrum. This is a discrete spectrum because you're only observing fixed wavelengths. And all of the other wavelengths are not visible, right? That's why the rest of the spectrum is black. So this would be called a discrete emission spectrum because we're looking at the light that is emitted from the gas. And all of the light that is emitted shows up as these colored streaks on our spectrum. Now say we pass light through a cold gas. So the cold gas will absorb light. And we do the same thing where we pass our light through a prism. Again, only certain wavelengths of light are observed in this spectra. And since only some values are possible, we call this a discrete spectrum. So notice at this time we're looking at absorption. So if the object absorbs the wavelength of light, then that means we won't see it. So that means we'll see a black area where that absorption occurred, and then the rest of the spectrum has all of the colors. So you can see that the discrete emission spectrum is actually the opposite of the absorption spectrum. That's just because that they're opposites of each other. Okay, and then this shows all of them together as a comparison. So hopefully this can clarify the difference between a continuous spectrum and a discrete spectrum. Okay, so someone asked, what properties of hot gas allow for the discrete emission spectrum? So we'll actually talk about that for the rest of the presentation today. So that is because there's energy levels that occur at very fixed energies. And this is a consequence of some of what Max Planck stated about quantization of energy. And so only the discrete values are shown because those are the only values that actually emit light. All of the other wavelengths are not emitted. And then someone said the prism absorbs the colors not seen in the discrete absorption spectrum. No, so the gas in the first place will only emit those 4 wavelengths of light. So all the prism does is it splits light into, so that we can observe it more easily. Okay. So I'll give everyone another 30 seconds to ask some questions, and then we'll move on. Okay, great. So all of these spectra are actually really important. So the atomic spectra is a type of measurement you can do to learn about elements. So atomic spectra use emission and absorption of light to provide information on atomic structure. And this is actually how people identify the composition of stars in outer space. So I quickly wanted to show a video of what these look like in real life because they're kind of cool. Okay, so I'll just show 2 of them, but if you're curious, this video shows a bunch of other elements, and they all have different atomic spectra, and they're kind of cool to look at to see all these colors that actually happen from these atoms. Okay, so why do spectral lines actually happen? So here's our hydrogen emission spectra, which is just like what we this is not how we detect stars, this is how we learn about the composition of stars. Yeah, because they can basically measure the emission of the different elements. So then you can say, oh, there's helium around this star because you can look at how like the light actually splits up. Okay. So classical physics actually predicts continuous spectrum for atoms, but discrete spectral lines actually occur. So why is that? Why do we only get these discrete lines when we take spectrum of atoms? And then how can we predict the wavelengths that these spectral lines actually occur at? So in order to answer these questions, we need to understand more about how emission and absorption actually occur. So just a quick review question. I have 2 spectra shown here. So which one is an example of a discrete spectra and which is an example of an absorption spectra? So I'll give everyone around a minute to think about this. And again, feel free to ask questions in the chat while working in groups. Okay, I'll give everyone around 30 more seconds and then we'll go ahead and go over this example. Okay, great. So first question, which example is a discrete spectrum? So we can see that the top one actually has all of the different wavelengths of light. So that would be a continuous spectrum. But the one on the bottom has this missing section in the middle of the green light. So because of that, we would call it a discrete spectra. It's not continuous, right? We have a break in the wavelengths that we are observing. So the bottom one would be your discrete spectra. And then which is an example of an absorption spectra? So an absorption spectra is when your material is actually absorbing some light. And when you're absorbing light, we know that our eyes will see black because that means that everything is absorbed and nothing is reflected for us to see. So that means that this is also an absorption spectra because we're seeing all of the other colors except for this one section where light is absorbed. So specifically, we're looking at the absorption in this spectra. So hopefully that clears things up. Well, we'll talk more about the differences between absorption and emission throughout class. So hopefully it'll make more sense if right now it's still a little bit confusing about the differences between them. We'll do a lot of examples to actually calculate them, and that will definitely help. Okay. So let's talk more about the difference between absorption and emission of energy. So we can think about this in terms of an energy level diagram. So on the left, I have an energy level diagram for absorption. So say that we have some electron that's at this low energy level. And then we have an incoming photon. So this incoming photon, like we learned yesterday, will actually deposit energy into our material. And this is the same thing as absorption. So when this material absorbs this incoming photon, it absorbs energy. And that energy causes an electron to move from the low energy level to a higher energy level, like seen here. And we know from what Planck discovered that this energy difference between these levels has to occur as a quantized value that's equal to Planck's constant times the frequency of light. And I just wanted to note here that sometimes I have the mu's for frequency and sometimes I have the f's. This is just because last class we used f because velocity was in a lot of our equations, but here I kind of use both sometimes, but hopefully it's clear. In all of the equations I write, I use f, but in some of the pictures that I got off the internet, there is mu for frequency instead. So if that confuses anyone, please ask to clarify the difference between the mu and the frequency if you're ever confused. But most of them are f's, but a few in pictures are actually represented as the mu's. So someone asked, does space absorb light? Do you mean outer space? Yeah, I'm not sure. If you clarify your question, maybe I can answer it a bit better. Okay. So just to summarize, an absorption, the incoming light or photon is absorbed by your object and then converted into energy. This energy promotes an electron into a higher energy level. On the other hand, we can also think about what emission is. So in emission, we would have an electron that starts out at a higher energy level. And then this electron is going to move into a lower energy level. And when this happens, you actually get a release of energy. And this energy is released as a photon. And this photon would have some given frequency that's related to the energy released during this emission. So just to summarize, emission occurs when an electron moves from a high energy level to a low energy level. And then energy is released when the electron moves to a lower energy level. And then this energy is emitted as a photon, right? Because we know that energy must be conserved. Okay, so someone asked to go over absorption again. So let me just go back and I'll also go over emission too. Okay. So we can think about absorption in terms of an energy level diagram. So say we have an electron that's in our material, and that's at a low energy level, so shown here. And then we have this incoming photon. This incoming photon or light has some energy. And that photon or light will hit our material and it will deposit its energy into the material. So when that happens, all of this extra energy from the photon will actually allow it to move to a higher energy level. And from what Max Planck stated, we know that this difference in energy between the energy levels must equal Planck's constant times the frequency of the incoming photon. So we'll clarify some of the math behind these equations later in class, but right now just focus on actually the difference between absorption and emission. Okay, so then to summarize, an absorption, your incoming light is absorbed by the object, and then that light had some given energy, and all of the energy from that light is then converted into energy within the material. And that energy within the material actually causes an electron to be promoted into a higher energy level, right? Because we know that all energy is conserved. So you can think of it like an energy balance, where you have your incoming light that has some fixed energy, and once the light has deposited its energy into the material, that energy has to go somewhere, right? So that energy, what that energy ends up doing is it ends up promoting an electron into a higher energy level, just because energy needs to be conserved. Okay. And then we can think about the same thing for emission. So in this case, we would have another electron, and that electron would drop down to a lower energy level. So when it does this, it actually will release energy. And again, this energy has to go somewhere, right? So what happens is this energy is actually emitted as a photon. And that's the light that we see, is the light that has actually been emitted. So then the emission will actually occur when an electron moves from a high energy level to a low energy level. And the energy is released when the electron moves from this higher energy level to a lower energy level. So if that's confusing, again, just think about conservation of energy. And then all of this extra energy that was released because the electron moved from a higher energy level to a low energy level is actually emitted as a photon. So hopefully this clarifies some of the differences and why we see light or don't see light in absorption versus emission spectra. But we'll continue to talk about these concepts throughout lecture today. Okay. So we're going to talk today quickly about the Bohr model of the atom. So Niels Bohr was a really important physicist in the early 1900s, and he used the information in atomic spectra to create a new model of the atom that was able to explain spectral lines. So basically, he applied Planck's concept of quantization to the electrons in atoms. And sometimes this is referred to as the quantization of electrons. And this was actually so important that he won the Nobel Prize for it. So this model was really great back in 1930. But a quick disclaimer is that although this model was a really important step in our development of the atom model, it's not correct anymore. But we still teach it because it's a great way of thinking about these spectra, and some parts are correct. So today we'll quickly discuss his theory, but then also some of the issues with the theory and kind of lay down the groundwork of some of the correct concepts later in class. But just have that in your mind, is that Bohr's model is great in some ways, and it's a great simplification to help us learn about these spectra, but it's not the correct model of the atom anymore. The correct model of the atom is all given by quantum mechanics, which is something you will learn quite a lot about in Chemistry 1A. Okay, so let's go over the Bohr model of the atom. No, was there a comment? Okay, so someone said, wait, so most things we learned this far are not true. No, all of the things learned so far are true, but they're better and more correctly explained by quantum mechanics. So we haven't talked about Bohr's model yet, but everything I'm about to tell you is 75% true. So everything we learned about the differences between emission and absorption is absolutely correct. And that is exactly how it works in quantum mechanics, and that is all true. So what I'm about to discuss today, or like for the next 5 to 15 minutes, that's specific to Bohr's model, that is all close, but not entirely accurate. But I'll be really clear about the things that are true and the things that aren't true. So we'll discuss that explicitly at the end. So hopefully that clarifies what is correct. Yeah, but this model still is really important and actually can predict all of these spectra exactly, which is why it's still taught today as sort of like an iteration along the way to learning about how atoms actually behave. Because how they actually behave is really very complicated. Okay, great. So starting off with Bohr's model, which is not entirely true. So what Bohr said is that electrons orbit the nucleus in fixed paths. So for example, we have our positively charged nucleus, which is the red dot at the center, and then we can draw lines that represent the orbits of electrons. So he said that each orbit has a fixed energy and distance from the nucleus, and we can label these orbits with numbers. So by convention, we would use n to describe the different levels going away from the nucleus. So the one that's closest to the nucleus, by definition, would be n equals 1. And this one would have the lowest energy, which will be more clear when we plot some of these things later. So then there are different levels that have different energies and distances from the nucleus. So for example, this could be one that's called n equals 2. And then you would have one that's called n equals 3. So again, the main part of how Bohr represented the atom is that all of the electrons are orbiting the nucleus in very fixed paths. And then each orbit has a fixed energy and distance from the nucleus. So for example, say we had an electron in our n equals 1. This electron is just going to be orbiting in this fixed path, right? So it's always going to stay in this path. Its radius is never going to change, and its energy is not going to change unless perturbed by an outside source. Okay. So then, so someone asked, is the cloud model the correct or more correct? Yes. So we'll talk about that at the end of class. So the correct way is to represent all of these things probabilities. So you can't say that an electron is in a fixed path and has a fixed energy. You can only say that there's a certain probability that an electron has this energy and a certain probability that you know where it is. So yeah, that's absolutely correct, is that the cloud model is the correct version for how we would describe these things. Okay. So commonly we can write the radius of all the electrons in orbit 1 using r with a subscript 1. And then we can also represent the energy of all electrons in orbit 1 with E and then n equals 1 at the bottom. So this is the most common nomenclature you'll see in textbooks. Okay. So from what we talked about before about emission versus absorption. If energy is absorbed, then that will allow an electron to move to a higher energy level. However, only certain amounts of energy can be absorbed because energy levels are quantized according to Bohr's model. This was the main innovation in his model, was that he incorporated the quantization of energy into this model. So what would this exactly look like? We would have our incoming energy, our photon, and this would be absorbed by the matter or by the atom, and all of the extra energy from the photon would promote an electron from n equals 1 to n equals 2. And this would be an example of absorption in Bohr's model. So now let's look and try to represent his model in a different way. So if you just take kind of a snapshot of these energy levels, just because it's hard to depict changes in energy with having to draw big circles all the time. So we're just going to think about just a small section and represent that using an energy level diagram. Oh, I forgot I had animated the electron to move around. N equals 2. Okay. So let's take a look at the energy level diagram. So this is just like what we saw on the last page, where we have n equals 1 that has the lowest energy. So the energy level that is closest to the nucleus has the lowest energy. This is by definition. Then we have n equals 2. This is the level that is the next farthest from the nucleus. And so it has a higher energy. And again, this is just by definition. Higher energy electrons are farther from the nucleus. And then n equals 3 is even farther above that. So in Bohr's model, if energy is absorbed, an electron can move to a higher energy level. So say again, we have our incoming photon, and that will deposit energy into our atom, and this energy will allow us to promote an electron from the n equals 1 to the n equals 2 level. And again, only certain amounts of energy can be absorbed because these energy levels are all quantized. So that means if we look at the change in energy between these two states, it has to occur in a quantized amount. So we can calculate the difference in energy between these energy levels by just taking the energy of the final state and subtracting it from the energy of the initial state. So another way of writing this in nomenclature that relates to the diagram is saying that your change in energy equals your energy of your electron in your second level minus the energy of an electron in the first level. So hopefully this makes sense. Again, feel free to ask any questions in chat and we'll try to answer them. Okay, so just a few quick concept questions. So take around a minute to think about this. When you move an electron away from the nucleus, what is the sign of delta E of the electron? Is it positive or is it negative? Okay, great. So we'll go ahead and go over this. So if you move an electron away from the nucleus, your sign of your change in energy would actually be positive. So if we think back to this slide, we know that energy levels that are farther from the nucleus have a higher energy level, and then the energy levels closer to the nucleus have a lower energy level. So if you think of the change in energy as your final energy minus your initial energy, then that would mean that delta E would have to be positive, just because we're moving our electron to a higher energy level when we move it farther away from the nucleus. So the answer to this would be positive. Okay. And then when you move an electron away from the nucleus, is energy required or released? So take a few minutes in your group again to think about this question, and feel free to also ask any questions about the previous question in the chat. And sorry about the background noise. My landlord is leaf blowing outside. It's great timing. Hopefully you can still hear me. Post it in the chat if it's really, really bad, and I can repeat some of what I said. Or I can go yell at the landlord. was wondering what you were doing. Okay, yes, they can still hear us. Okay, great. So we'll go ahead and go over this one. So when you move an electron away from the nucleus, is energy required or released? So when you're moving, yeah, no, it's my landlord's leaf blower. He does it like every week. It's very sad. I'll just try to talk louder. So when you move an electron away from the nucleus, you're moving it to a higher energy level. And since it's gaining energy, it actually requires energy to do, right? So if you think about if you're picking up a brick and you're moving it to a higher height, that requires energy for you to do it, or it requires work. So the same thing is true of atoms. When you're moving an electron farther from the nucleus, it requires energy to do that. Okay. So we can also relate the energies in the Bohr model to the energies of our incoming photons. So again, just to review, we can calculate the difference in energy between the energy levels because we know the energy of the final level, and we can subtract that from the energy of the initial level. So this can just be written as your energy at n equals 2 minus your energy at n equals 1. And we know that because this incoming photon is exchanging energy with our atom, that this change in energy must equal Planck's constant times the frequency of your incoming light. So I'll give everyone a few, like around 30 seconds to ask any questions about this, because this is a really important concept moving forward. So to summarize, because our incoming photon is exchanging energy with our atom, and we know that these energy levels are quantized, we know that the energy of our photon must equal the difference in energy between these two levels for this transition to actually occur. Okay, I'll go ahead and move on, but again, feel free to ask any questions. So there's actually some empirical relationships that allow us to calculate the frequencies of light that cause these transitions. So one of the most used ones is called the Rydberg equation. So this one actually allows us to calculate the energy difference between orbits, but here I've simplified it so it just shows the frequency of your light and how that relates to your change in energy levels for the atom. So here you have a constant out front. This is called the Rydberg constant, and it's defined to be 3.29 times 10 to the 15th hertz. And then you have the integer number of your initial energy level and your integer number of your final level. So these would be the same numbers that we read off of our energy level diagram. So for example, n final could be n equals 2 and n initial could be n equals 1, but they are always integer values. So this empirical relationship actually allows us to calculate the observed frequency of light when atoms undergo transitions between these different energy levels. So this is a lot of information at once, but we're going to go through an example to help kind of clarify how this relates to the spectral lines that we talked about at the beginning of class. Okay, so I'll give everyone a quick minute break, and then please ask any questions, because then we're going to move on and we're going to do an example, and we're going to actually calculate the spectral lines of the hydrogen atom that we saw in the video. Should be kind of cool. Okay, so someone asked, how do scientists determine the equations and constant values? Is it more of a hypothesis derived from experiments? The accuracy of the constant surprises me. So I do often round the constants I give you, so I think it does go out to more decimal places, but it still was empirically derived, so that means it was like fit to actual data. Um, it was determined purely experimentally, but now that we know more about physics, we can actually um, go back and derive these relationships and understand why you have like n squared in this equation. But back when this equation was first proposed, they didn't know that. But with some of Bohr's work and some of the work by later physicists, you can actually go back and derive all of these equations. So now they are derivable, but at first they were a really educated guess of how these things worked. Are the n values the level number or the amount of electrons on the level? So they are the level number. So that would be like, if we go back to this slide, that would be like the n equals 1 level, or the n equals 2 level. So the amount of electrons in each level is not relevant for spectral lines. It's just the energy of the transitions that matters. Yeah, I see that the way I phrased that was a bit unclear, but I mean the n equals 1 number, not the number of electrons. So just the number of the actual level. Yeah, and also all of these slides are posted on B courses. So if where we are going through a lot of information, so sometimes it can be helpful to have the slides like printed out or on the computer where you can type or write notes as we go through these things. Just because, yeah, I mean, it's hard to actually write down all of the things that I'm saying and all of the things that are on the slides at once. I realize that, so we try to post the slides online right before lecture so that you can reference them during class. Okay, great. So let's move on to some calculations. So what we're going to do is we're going to calculate the hydrogen emission spectra. So I have showed the emission spectra of hydrogen here. So we can see that there are 4 distinct lines that occur at 4 distinct wavelengths. And again, we are calculating the emission spectrum. So this is when the electron moves from a higher energy level to a lower energy level. And in this process, it emits a photon that has a given frequency. And it is this photon that we are observing in our with our eyes or with our spectroscopy experiment. So that emitted photon is what actually gives us the information about these lines. Okay. And as a reminder, the electron will release energy in the form of an emitted photon when it moves from this high energy level to a low energy level. So that's what's happening in our atom, and then this causes the photon to be released, and then the released photon is actually what we are detecting in spectroscopy. So hopefully that makes sense with what we talked about before. Okay. Then we're going to try to find wavelength in all of our calculations today, but Planck's relationship is written in terms of frequency. So to make things easier, I'm going to make a few substitutions in class, and I'm not always going to show the rearrangement just because I trust that everyone can do that based on what we did this week and what I'm about to review now. So we know that the velocity of our light is equal to the frequency times the wavelength. And again, for all light in the electromagnetic spectrum, it will move at the speed of light. And we often call this c, just because it's a constant that's known. And as a reminder, c is something that you can always look up or will be given to you, or you will be directly told to memorize it, but it's 3.00 times 10 to the 8th meters per second. And then we can rearrange this equation to get an equation for frequency. So frequency equals the speed of light divided by our wavelength. And then we can substitute this into Planck's equation to get an equation that's in terms of wavelength instead of frequency. So that would give that our change in energy is equal to Planck's constant times the speed of light divided by the wavelength of light. So just keep that in mind. Okay, so now we're going to look specifically at the Bohr model of the hydrogen atom. So to calculate the spectra, we need to consider 6 different energy levels. So we have n equals 1, that this by definition is closest to the nucleus, and it is at the lowest energy. Then we have n equals 2, n equals 3, n equals 4, n equals 5, all the way out to n equals 6. So these are the ones that are going to be important for us today to do our calculation. And as a reminder, the hydrogen atom only has 1 proton and 1 electron. If that is confusing, make sure you go back and review some of the material from week 1 or come and talk to one of us. So if you look at the periodic table, you can get the atomic number and all of the information about hydrogen, and that will tell you that it has 1 proton. And because atoms must be neutral, or at least the atom we are talking about now is neutral, that means that if you have 1 positively charged proton, you must have 1 negatively charged electron. So that is why the hydrogen atom, has 1 proton and 1 electron. So let's say our electron exists on the orbit that's at level number 3. So that would be at n equals 3. Someone asked, why are we only considering 6? Because those are the only transitions that occur in the visible region, so they're the only ones that we would observe using visible light spectroscopy, but there are others. And you can also calculate those using equations. But we're just today only going to think about some of the lower energy ones. Okay. So to make things easier to represent, again, we're going to plot all of these different energy levels or orbits as a function of energy using lines instead of having all of these circles around in our diagram. So that would look like this. So then we can propose the following question. We can try to calculate the wavelength of light emitted when an electron moves from the n equals 3 to n equals 2 energy level. So just to visualize that, it would be like this. So your electron would start out in your n equals 3 level, and then it would move to your n equals 2 level. So here I've given the Rydberg equation again, and then some of the constants and what all of the numbers mean. So please take around a minute or 2 to calculate this as we go along, and I'll go over the answer in a minute. Okay, great. So, someone asked, what does F represent in this equation again? So F is frequency. Yeah, great question. Sometimes I use mu, but in most of the written equations, it's all frequency. But we are trying to calculate wavelength in this problem, not frequency. Give around 30 more seconds and then we'll go over it, just because we're reaching the end of class. But all of these are also homework problems, so then feel free to go through them as well if you didn't have time to complete them during class. Okay, great. So we'll go ahead and go over this. So to solve this, you would need to know the number of your final energy level and the number of your initial energy level. So the no is that equation saying F is equal to the Rydberg equation. Yeah, so the Rydberg equation actually is that frequency equals this constant times all of these other energy level numbers. So the Rydberg equation is the F part. What I inserted was that frequency also equals the speed of light divided by wavelength, just because we are trying to calculate wavelength in this example. But the Rydberg equation is, let's see, it is exactly what is here. So it would be F, which is frequency, equals this constant, and then multiplied by the quantity that relates to the number of your energy levels. So there are several forms of the Rydberg equation, and some of them will actually have it in terms of energy instead of frequency. So definitely if you look at textbooks, you will see that. And then sometimes they'll have a different constant for that as well. So just make sure you're aware of which one you're using if you look at another textbook. Someone asked, how does Rydberg's equation apply to other atomic models? So even in like the correct models that use quantum mechanics and probability to describe electrons, there still are these numbers that relate to your levels. So you'll learn more about this in Chem 1A, but you still would be able to use his equation. It actually works very well at predicting the spectra of hydrogen. It just breaks down, or it doesn't break down, some of the reasons why it worked according to Bohr are not correct, but that doesn't mean that this empirical relationship still isn't a good representation of how atoms behave. Okay, so I'll go ahead and go over the example. Let me just go back. Okay, so to calculate the wavelength, you would need the speed of light divided by your wavelength, and that would equal the Rydberg constant divided by 1 over 2 squared minus 1 over 3 squared. So in this case, your final energy level is n equals 2. So that's why we have a 2 squared. And then your initial energy level is at n equals 3. So that is why you have the 3 squared. And again, I simplified this so that we can calculate wavelength directly instead of having to calculate frequency and then calculate wavelength. So I didn't go through all of the algebra, but this does give an answer of the wavelength being 6.57 times 10 to the negative 7th meters. And then you can convert that to nanometers. So that would be 657 nanometers. Okay. And if we look at our emission of spectra of hydrogen, we actually see that there is a line right at 657 nanometers. So this is great. That means that the Rydberg equation was actually able to calculate the emission spectrum of hydrogen. Someone asked, is that a negative sign in front of the Rydberg constant? Yes. So that has to do with the sign of changes in energy going from between emission and absorption. Because we're just calculating frequency, it doesn't really matter, but there is a negative sign. So if you ever asked to calculate the change in energy, then you would really need to think about that and take it into account. But for us today, it doesn't matter so much, but there is a negative sign. Okay, great. So looks like we're running a bit short on time, so we won't do this practice calculation today, but it is also in your homework. So I encourage everyone to go and calculate this example as well. So the Bohr model of the hydrogen atom actually is able to predict every single atomic spectra transition that we observe. If we go back here, you had a red line, a light blue line, this purple blue, and then this dark purple line. And those would correspond exactly to what we would get if we looked at the transitions between n equals 2, n equals 3, between n equals 2, n equals 4, and between n equals 2, n equals 5, and then the final one is between n equals 2 and n equals 6. So someone asked if there are other transitions. The answer is yes, absolutely, but these aren't observed in your spectrum. So that's why we only talked about these today, is because our goal was to actually exactly calculate this entire emission spectrum, which we would be able to do if we just looked at the transitions between those 6 energy levels. Okay. So briefly, just as a reminder, there are a lot of failures of the Bohr model. So Bohr's model actually only works for atoms with 1 electron, which means it only works for hydrogen, which isn't really great for a model if you're trying to model every single atom. And that is why all of our examples were about hydrogen today. So that was a big failure, is that this model actually only was able to correctly predict for 1 element. And the reason for this is that the model actually treats electrons as classical objects. And this isn't true, right? So in his model, all of these electrons are orbiting at a fixed known distance. And that just isn't representative of the way that we think about electrons now, because we should treat them instead with quantum mechanics instead of with classical mechanics. So there's quite a few more failures of the Bohr model, but these are the main ones. But if you're more curious about some of the intricacies of this, I encourage you to look up some of that information or talk to us after class and we can explain more. But the main issues, again, were because they modeled electrons as classical objects, and that caused a variety of issues, and that's ultimately why we are only able to predict hydrogen or atoms with 1 electron with this model. Yeah, so this is all because it doesn't obey quantum mechanics. So speaking of quantum mechanics, one of the main statements that comes out of quantum mechanics is the uncertainty principle. So this is called the Heisenberg uncertainty principle. And this principle states that the location and momentum cannot both be precisely known. So this means that we cannot simultaneously know the radius and energy of all of our electrons in our atom. So this is why the Bohr's model failed, is because of this uncertainty principle. The things that he said we knew, we just couldn't, right? And it's impossible for us to ever precisely know both the radius and the energy of our electrons. So this can be expressed mathematically with the following statement. So don't get too bogged down in details here. The main takeaway is that we can't know the location and momentum precisely, but we can write that in a form of this equation. So this is just saying that your change in momentum, so your uncertainty about your momentum times your uncertainty in distance or location will always be greater than this fixed value. So that's saying that you always have to have some degree of uncertainty. So that equation can be a bit confusing, so definitely let me know after class if you have more questions about it. Okay. And the main takeaway of this is that we can only know the probability of an electron's location and its momentum or energy. So back in week 1, we talked about sort of this cloud model that I depicted using this shaded like circle. So that is actually the reality, is that we don't know exactly where these electrons are, but they are not in fixed orbits that have a known energy. They're just simply somewhere around, and we can calculate the probability of where they are, but we will never exactly know where they are. So this is one of the main takeaways of the failure of Bohr, and also how we are going to think about chemistry moving forward. So in Chem 1A, you're going to start off by thinking about some of these principles and then using more complex equations to actually describe an atom. Okay, great. So that was all the material we had for today. We were a bit short on time, so I had to run through the end a bit quickly, so definitely feel free to stay in office hours afterwards for any questions, or reach out to us or the tutors as well. But we'll go ahead and bring everyone back into the main Zoom room for office hours.